I guess one thing to start with is I know this is like a network seminar, and so I most of my research has been in applied topology, and so I think maybe this is one of those talk titles where you look at it, and some of you might not be familiar with everything in the title, such as what this word means or what it means when this word comes before it. So, uh, kind of the first thing I want to do in my talk is actually I want to spend about half of it just explaining at some level what persistent homology is. But even without knowing what it is, the point of this talk from the title is there's this operation called persistent homology, and it can act on point clouds. And I'm interested in the level sets of persistent homology. So uh, if I look at one particular output of persistent homology, what are all of the different point clouds coming in that give me the same output? Okay. Um, so. All right, the first thing that I need to do is explain homology. And this is a thing that kind of traditionally came from like algebraic topology. And the idea behind it is that it's something that can tell you about how many holes there are in a shape. And this turns out to be something that's actually pretty difficult to define. So I'm just going to go over it kind of lightly, I guess at a more intuitive than technical level. And I'd encourage you to think about, how you would maybe define a hole in a shape that's uh, more complicated than a graph, say. And you'll see that it's actually quite difficult. Um, but okay, so at some technical level, when people think about homology, you need to fix a choice of field. And if that's sort of unpleasant to you, just pretend every time you see a capital F in this talk that this is just the real numbers. Although in practice, usually it's Z mod 2. Um, okay. And so for every non negative integer, you get an operation called HI, or the ith homology. And it takes in shapes, and by shapes I mean topological spaces, and it returns vector spaces over your field F. Okay? Um, and what does it do? Well, uh, if your space has n path components, then all h0 of x will return is it'll give you a vector space that's n dimensional. So like if I look at this shape here, this shape has three path components, and so h0 of it gives me a three-dimensional vector space. Okay. Um, Now what about positive I? Well, these are a little harder to there's no such nice theorem that kind of quickly tells you what uh, what these things are. Well, but I'd say one way of interpreting hi of x for positive I is that it's telling you about the number of I-dimensional holes in your shape. So, uh, for example, if your shape is convex, it turns out that all of the higher degree homology vector spaces are going to be trivial because there's no holes in a convex shape. So, like H1 of the solid disk has to be trivial because the solid disk is a convex shape. It has no holes. Um, I guess the way that I think of H1 is that it kind of tells you about like the number of holes in your shape that you could punch through. So, like a circle has one such hole, and indeed, uh, H1 of the circle is a one-dimensional vector space. I guess since this is a network seminar, if I have a graph, H1 of your graph is going to give you the Betti number of your graph, the number of loops in your graph. Um, okay, what does H2 do? Well, H2 is kind of telling you about like the number of voids in your shape. So think like, a hole in, I saw one paper that described it as like, the holes that you may find in Swiss cheese, for example. So a two sphere has like one such hole, and indeed H2 of the two sphere is a one-dimensional vector space. Um, in general, like an n-dimensional sphere, if you go through how to compute these things, it turns out it has an n-dimensional sphere has one n-dimensional hole, or at least that's what homology says. Um, so I don't want to go into any more detail about that because the definition of this is a little cumbersome and takes a while to get some intuition about. Um, the other thing that I want you to know, though, about this kind of theory of homology from like abstract algebraic topology is, if anytime you have a continuous function from one topological space to another, you get a linear map. Okay, so like a linear map between the vector spaces given by ith homology. So what we'll care about is when f is an inclusion. So we'll be particularly interested in like sequences of shapes like this, you know. So here on the left, I have a shape with one-dimensional hole. In the middle, I have a shape with two one-dimensional holes, and on the right, I have one with once again one-dimensional hole. And so H1 not only gives us vector spaces that tell us the number of one-dimensional holes in my shape, but they also explain, which hole winds up where as I grow my shape. Okay. Um, so uh, I think I can assume that you are comfortable with simplicial complexes in a network seminar, so I'll skip these slides. Okay, and now I could get to uh, kind of the maybe classic motivating case for persistent homology, which was like, imagine, you have this point cloud that I've drawn here in R2, or maybe more generally, some other point cloud in R to the D. Well, if I just naively apply um, homology to this point cloud, it's going to say that I have nine disconnected pieces and zero holes, which is not very interesting. There's 9 points in this point cloud. Um, but if I were to thicken this point cloud a little bit using a simplicial complex structure, now I have a new shape that has one-dimensional hole and one connected component. All right, it looks like a circle. Um, so people got kind of interested in this, and so if I want to do something like this, I need a principled way of thickening point clouds. And I will tell you two classic ways of thickening a point cloud. So one is using what's called a check complex. So this is where you start with you give me a point cloud, you give me a positive number r, okay, and then I give you back the simplicial complex containing the point cloud, and then any tuple of points that are contained in a disk of radius r. Okay, so for example, if I were to see these 3 points in my point cloud, and I observed that they could be contained in a disk of radius r, I would include the triangle in my check complex at radius r. Uh, the other way of thickening a point cloud that's kind of most popular is what's called the Vietoris-Rips complex. So what this is, you give me a point cloud and you give me a positive number r, and then I give you back again the simplicial complex containing my point cloud and any tuple of points that are pairwise 2r or less apart. Right, so now if I see these 3 points, I include the triangle between them if I observe that all three edges connecting each of them is less than or equal to 2r in length. Okay. Um, so so that solves one problem, and now there's another problem, which is that in either way of thickening my point cloud, I have this choice of a number r. So which r am I going to pick? Well, um, one thing to note is that as I increase r, either way, whichever strategy I'm using, my simplicial complex is going to get bigger when I'm increasing r. So this means that at the level of homology, I get a linear map between the vector spaces given by increasing the radius. Okay, so by varying R all around, you get something called, or you get a bunch of vector spaces that are connected by linear maps, right? Anytime you have an increase in R, that corresponds to some linear map. right? And this is true for check and Vietoris Rips constructions. And such a thing, a collection of vector spaces that are connected by linear maps for any time you increase the index. This thing is called a persistence module. This is just the technical language that people use in computational topology. So, like the summary of like what I've said so far is like, you know, you have your point cloud, and then by increasing R, you get an increasing collection of simplicial complexes. And then by applying H1, you get this persistence module, right? This collection of vector spaces connected by linear maps. Um, so let me give like uh, a very simple example of a persistence module that's just purely abstractly defined. And then we'll see that it's actually quite an important example. So the example I want to give is what's called an interval module. So you give me an interval, and then I'll give you back a persistence module. Okay, so if you give me the interval I, then the idea is if I look at what my persistence module is doing at index R, it will give me a copy of a one-dimensional vector space. Uh, Otherwise, it'll give me a copy of a zero-dimensional vector space. And then the linear maps basically are going to be the identity everywhere they can, and will be the zero map everywhere they can't be the identity. So like in a picture, like if this is the real line with my interval I on it, this persistence module, this interval module will give me a copy of a one-dimensional vector space every time I'm in I, and a zero-dimensional vector space every time I'm outside of I. And then, this linear map from this lower index to this higher index will be the identity, and all these other ones will be the zero map. Okay. So, um, the reason that I care is because there's this technical result by Zomerodian and Carlson that says that if a persistence module comes from, I mean, it says a little more than this, but for the context of this talk, what I care about is that if a persistence module comes from either this check or Vietoris-Rips construction, then it decomposes into a direct sum of these interval modules. Okay, and if that's too confusing, like basically the only thing I want you to know for this talk is that like okay, so I have my collection of simplicial complexes that I've gotten by say the Vietoris-Rips construction. What this theorem says basically is that I can describe this canonically by a collection of intervals. Okay? So these intervals say the following. First, there are no holes. Then at R1, a hole appears, and then it disappears at R2. And then at R2, a new hole, distinct from the one we had before, appears, which then disappears at R3. Okay? So this is giving us more structure than we originally had, because it's telling us not only that there's a hole at R1 and R2, but actually the hole that appears at R2 is distinct from the one at R1. Okay? So this is what persistent homology is. You give me an index I, and then I apply ith homology to my check or Vietoris-Rips filtration, and out comes this collection of intervals, which people call barcode. Okay? Um, so this is like the setup of my talk. So here's a point cloud. It's an ordered point cloud of n points in d-dimensional space. So here n is 3 and d is 2, right? 3 points in two-dimensional space. I'll denote point clouds with a capital P. And I'll denote the space of point clouds as PC. And for not very interesting technical reasons, I won't allow distinct points in my point cloud to overlap. Okay, and what I just said is that you can apply this persistent homology with respect to either your check or Vietoris-Rips filtration. And this will give you a collection of intervals describing the degree 0 homology, the degree 1 homology, the degree 2 homology, and so on. And I guess in this picture, maybe there are no intervals describing the degree 2 and so on homology. Perhaps there's no holes of degree higher than 1 that appear when I do my filtration in this example. Um, so some other notation I'll use. I'll refer to the degree 0 collection of intervals as D0 or pH0 of P. The degree 1 intervals as D1 or pH1 of P. And I'll call the whole thing D or pH of P. Okay. S- uh, so as I think I said verbally earlier, people in this realm, for some reason, have decided to call a multi-set of intervals a barcode. So that's the language I'll use. I'm also going to use slightly non-standard language, which is that I'll call this collection of barcodes in each degree. I'll call this thing a full barcode. So that's not standard language, but I just want to make the distinction between am I thinking about a collection of intervals describing one particular kind of hole, or am I thinking about all of them simultaneously? Okay, so that's what persistent homology is. That's some of the jargon. What I'm interested in this talk is you give me a collection of intervals in each degree, and I want to know what's the subspace of point clouds with a full barcode D. Okay? And in particular, what I'd like to know is I'd like to know how big this space is. So if this space is really big, then what that means is that persistent homology is sending a lot of different point clouds to the same output. Okay? But if it's very small, then that means that it's not sending very many point clouds to the same output. And so I want to use this as a proxy for descriptiveness, right? If this space is large, it's not being very descriptive at that output. And if this space is small, it's being pretty descriptive at that output. Um, and so as a proxy for asking how large the space is, I'll be looking at what's the dimension of this space. Okay. Um, and in particular, the reason I care about the dimension is this is telling me, how many ways could I take a point cloud with a particular full barcode and perturb it without changing its persistent homology. Um, okay, so this is based on joint work with Jacob Legany, Uzu Lim, Louis Theron, and Heather Harrington. It's currently on archive. Okay, so I was sort of surprised going into this, how little information I could find about the dimension of this space. So I'll tell you what I already knew going into it. The first is a well-known fact, which is that persistent homology is isometry invariant. So if I translate, rotate, or reflect my point cloud, that's not going to change its persistent homology with either the Checker-Vietoris filtration. Um, this is something that we like, by the way. We like that persistent homology doesn't change under these uh, alterations of our point cloud. The other thing I know comes from this paper by Smith and Curlin. And really, all they do is they study point clouds that have trivial or identical degree 1 persistence. Okay, and so one thing that they showed is that point clouds that lie roughly on a straight line, in some sense I don't care to make precise in this talk, um, that such a point cloud has to have trivial degree 1 persistence. And they do a little more than this. They attach this point cloud to other point clouds and show that if you do this in certain ways, it won't change the degree 1 persistence. Okay. Well, what I would like to do is I want to give an upper bound on what the dimension of these level sets could be. I would like to give a lower bound, a generic lower bound, on what the level sets of this dimension could be. And then I want to give an excuse for why they're not the same and why I think that actually computing the dimension of this is really hard. In particular, I'm going to look at a question that's seemingly easier, and I'm going to show that that easier question is actually quite difficult. Um, so, okay, so let's do the upper bound first. So here I'm going to use a folklore result, which is that if you given any point cloud P, the edge lengths of any minimal spanning tree of P are the bounded degree 0 right endpoints times 2. So, like in a picture, Like if this is my point cloud and then this is the barcode I get in degree zero. So, maybe it has these three bounded degree zero right endpoints, R1, R2, and R3. That means I can find a minimal spanning tree of my point cloud with edge lengths 2R1, 2R2, and 2R3. And this is something that's true for both check and Victoria-Swift constructions. And proving it, we wrote a proof, although we're sure it may have existed somewhere. It amounts to Kruskal's algorithm, so it's not a particularly deep folklore fact. Um, Okay. But this was super useful to us because this now is like a huge constraint on what our point cloud could possibly be doing if it has a certain degree zero barcode. So we use this to our advantage to get an upper bound. So the subspace of point clouds with a tree of pairwise distances fixed has dimension nd minus n plus 1. This is something that you can show. And then the folklore result says that every point cloud with degree zero barcode D naught has some spanning tree with edge lengths given by D naught. Since there are only finitely many such spanning trees, point clouds with degree zero barcode D naught actually have to lie on of a finite union of ND minus N plus one dimensional spaces. So this implies that the dimension of the level set of D has to be less than or equal to ND minus N plus 1. Okay. The lower bound is a little trickier. So I'm going to say some nonsense and then I'll draw a picture that hopefully clarifies what I'm saying. So what I'm going to do is I'm going to pick a relation on the simplices of the complete simplicial complex with n vertices. And these three rules just mean that this relation is going to act like a total order, except that different simplices are allowed to be tied. So that's what this or both is saying. Different simplices are allowed to be tied in my total order. So, like for example, if n is 3, then my complete simplicial complex is a triangle. And like this would be an example of a potential relation to choose, right? So first my 3 points, then this one edge, then this other edge, then the final edge in a triangle. Um, uh, okay, so it turns out that by picking such a relation, you actually carve out a subset of point cloud space. Okay, so the special set S, sorry, so the space is given by uh, all of the different point clouds where when I do my either check or Vietoris Rips construction, depending on which one I'm looking at the moment, all of the point clouds that are whose say check complex is appearing in the prescribed order. Okay, so uh, and so like maybe I look at these 2 point clouds. These 2 point clouds are in my nice set S corresponding to my relation. If for both point clouds, first the 3 points appear, then this one particular edge appears, then this other edge appears, and then finally the triangle and the third edge appear. They're allowed to appear at different times between P1 and P2, but the simplices need to appear in the same order. What that means is that the topology of the complex is going to change in the same order across P1 and P2. Okay. And so in some sense, I care not to make precise. This means that barcodes coming from point clouds in this nice set are going to be combinatorially equivalent. So you can get the barcodes of, say, P1 by sliding around, in some sense, the barcodes from P2. Okay. Um, and so what that means is that actually all that persistent homology does is it records the values of simplices that appear and change the topology. So like if we look back at this picture, like okay, so first the 3 points appear. And I guess each of these points gives you a connected component. Then when this edge in the top right appears, this is getting rid of a connected component. It's going to change H0 because it's going to kind of merge two path components in my simplicial complex, and the same is going to happen when this edge in the top left appears. But actually, these two, this triangle and final edge, neither of them, when they appear, they're not changing the topology of the complex in some precise sense. And so
Mm.
persistent homology isn't going to record when they appear. So really all it's going to record is, that the points are appearing at time zero or at r equals zero, and then it's going to record when the two edges appear. Okay. Uh, and so this sort of phenomenon works in general. And so this trick has been used before in a paper by Carrier and others. And so what it shows is after doing a little bit of work, you can use this fact to show that in some sense, persistent homology acts like a what's called a semi-algebraic function on each of these sets. And these are just certain kinds of well-behaved functions that people in real algebra like. Uh, and, you know, uh, so using results about the generic dimension of level sets of these functions, you can get pretty easily that for any generic point cloud in point cloud space, if k is the number of distinct non-infinite endpoints in the full barcode D, then the dimension of the level set at D is going to be greater than or equal to nd minus k plus 1. So the reason that the number of distinct endpoints comes up is that this is the number of like different um, uh, times that simplices appear and change the topology in the filtration when I'm in this nice set. Okay, so these bounds in general are quite far apart, right? So we have a minus n plus 1 on one end, and then we have that's an upper bound. And then we have that generically, the dimension of this space is bounded below by nd minus k plus 1. Okay, and these bounds agree when n is k, but it turns out that this will only happen when the degree I persistence is trivial for all positive I. So, and uh, going back to the interpretation, that means that there's never any holes in the complex. But in general, I wouldn't really expect for that to happen. So now I want to justify why I'm bounding instead of computing the dimension of this space. And I want to justify that by looking at an easier problem and then showing that it's kind of difficult still. So instead, I'm just going to look at what point clouds are best described by persistent homology. So uh, for the time being, what I'm going to ask is which point clouds have that for any sufficiently nearby p prime uh, with the same full barcode is p prime isometric to p. So like in a picture, if this is point cloud space, you can see the point cloud P sitting in point cloud space. When can I find a neighborhood around P where any other point cloud that's sufficiently close and has the same full barcode is actually isometric to P? So translation, rotation, and reflection away. Well, if P satisfies this, I'm going to call it locally identifiable under either check or Vietoris-Rips persistence. Okay, and for the time being, I'll focus on the Vietoris Rips case. And I'll come back to the check case if I have a little time at the end. Um, okay, so if my point cloud is generic, we can assume that it's interior to one of these nice sets that I defined earlier. So this is something that's pretty straightforward to prove. And I'm just going to take for granted for now. So in these nice sets, all homology is doing is it's recording when certain simplices appear, right? It's recording when certain simplices come in because these are the simplices that come in and change the topology. So for nearby point clouds P prime, the condition that P prime has the same persistent homology as P just means that certain simplices are appearing at the same time across P and P prime. Okay. Well, uh, it turns out that when you're doing the Vietoris-Rips complex construction, anytime any simplex appears, an edge has appeared at the same time. And because we're in this set where actually the edges are always appearing in the same order, it turns out that anytime a particular simplex appears, as long as I'm in the set, a particular edge is appearing at the same time. And so following your nose with this logic, you motivate a definition and a theorem. And so the definition is what I'm going to do is I'm going to take my point cloud P and I'm going to make a graph. And I'm going to make a graph by taking every edge that appears when the topology is changing in my Vietoris-Rips filtration. Okay, and I'll call this graph the critical graph of my point cloud. So so now I've taken my point cloud, I've made a graph with all the edges that come in and change the topology. And so the theorem that we were able to prove is that a point cloud, a generic point cloud, is locally identifiable if and only if P equipped with this graph is rigid. Okay, so what do I mean by that? Well, a point cloud equipped with a graph is rigid if the only ways to perturb P while maintaining the edge lengths of G is to perturb P by isometries. So this is a very physical notion. So let me draw a picture. So like this graph on the left is not rigid, okay? Because I could perturb this graph or this point cloud in like a bird flapping motion, I guess, or like a joint motion. And that would maintain the edge lengths of the graph, but would not be an isometric transformation of my point cloud. Meanwhile, this graph on the right, I would say is rigid in the plane because the only way I could perturb this graph while maintaining the edge lengths of the triangle is by perturbing it by either a translation or a reflection or a combination of the two. Okay, so given a point cloud, we're able to equip it with a graph whose rigidity generically determines if that point cloud is locally identifiable. Okay, if it has this very nice property where all nearby point clouds with the same output are actually isometric. Okay, so that's still not quite. This is anyway. Local identifiability is really a statement about the local dimension of my level set. Okay, so this is like a strictly easier problem. So what if I ask about the a non-local version of identifiability? Well, this is just what's called regular identifiability, and it's the same as local identifiability, but without the word nearby. But let me write it out anyways. So a point cloud P is identifiable if for any P prime with the same full barcode as P, P is isometric to P prime. Okay, so in other words, if P and P prime have the same output, they're isometric. So what this means is that if P is identifiable, the level set that it's in is just the isometry class of P. Okay, so this would mean that really persistent homology is maximally descriptive at P. We know that it can never tell apart isometric point clouds, and if P is identifiable, this means that isometric point clouds are the only point clouds with the same output as P. Okay. And to extend this kind of like rigidity theoretic understanding of persistent homology, you need some sort of non-local analog of rigidity. And so that's the notion of globally rigid. And we say that a point cloud equipped with a graph is globally rigid if any other point cloud with edge lengths given by G are isometric to P. So for example, this graph on the left is flexible. It's not even rigid. This graph in the middle with this point cloud is rigid. Okay. I can only perturb it while maintaining edge lengths of the graph by translating and rotating it. But if I'm allowed to teleport the vertices of this graph, I could do so in a way that preserves the edge lengths and isn't an isometry. Namely, I could teleport this vertex in the top right to the bottom left. Like I could fold this graph over on itself, and that would maintain the edge lengths, but wouldn't be an isometric uh, transformation of the point cloud. Okay, and this graph on the right is globally rigid. Okay, this is so not even if I'm allowed to teleport these points, the only way I can do so while maintaining the edge lengths of the graph is by isometry. So a translation, rotation, and a reflection. Uh, Now, in this particular example, this graph is complete, and that's why it's globally rigid. It turns out when you have more points, in the plane, you can have, or actually in any dimensional space, there's globally rigid graphs that are not complete. Okay. But just to give a simple example, I kept it with 4 points. Um, so what we're able to show is that when n is greater than or equal to d plus 2, and d is greater than or equal to 2, if I have a generic point cloud and p equipped with the same critical graph from earlier is globally rigid, then my point cloud is actually identifiable. Okay, and I want to make two notes about this. So first of all, um, this proof relies on similar ideas for the local result, but it also relies on quite a technical and modern result in rigidity theory from Gortler, Theron, and Thurston in 2019. And the other thing to note is that in my previous theorem about local identifiability, I had an if and only if statement. So I could really generically characterize local identifiability by looking at this particular graph and its rigidity properties. Um, but here we just have an implication. So we don't know if the converse of this is true. That's an open problem, and it seems quite difficult. Uh, okay, so I think I was asked to give 40 minutes talk, but I could do more, so I'll just leave it up to you. Uh,
Yeah, keep going. We have
okay.
so
Okay, cool. I wasn't sure. Then I have a few more slides. So I'll talk a little bit about the check case. So the check case is actually a little more complicated. So we can't say quite as much. Um, okay, so um, I guess let's recall one thing, which is that a simplex corresponding to a subset Q of a point cloud appears in the check filtration at the radius of the smallest enclosing sphere of Q. So like if this is, if I'm interested in when the triangle connecting these 3 points appears in my check filtration, well, it's going to appear at the smallest, at the enclosing radius, or at the radius of the sphere enclosing the 3 points. And this is called the enclosing radius of Q. And one thing that turns out to be technically useful for us is that it's the enclosing radius function isn't such a terrible function. It's there's a piecewise rational function that returns the squared enclosing radius of a point cloud Q. Okay. Um, so we wanted to kind of proceed analogously by like doing some sort of rigidity theoretic characterization of local identifiability. But it turns out that you can't get away with just looking at edges in the check case. The reason being that in the Vietoris-Rips case, anytime a simplex appears, an edge appears at the same time. That's just not true in the check case. What turned out to be the right definition is what follows. So a subset Q of my point cloud is called critical if the enclosing radius of Q is an endpoint of the persistent homology of P. Okay, so it appears at the same time that the topology changes, and every subset of Q has a smaller enclosing radius. Okay, so none of its kind of like faces are appearing at the same time. Okay. The critical subsets, okay, they're not going to form a simplicial complex. They're going to form a hypergraph on our point cloud. Okay. And we call this the critical hypergraph of P. So these are the simplices that appear, and they, in some sense, change the topology. Um, and so then we made up a new rigidity theory for these hypergraphs. So this isn't something that had been considered before. It appeared to be new. So, we let H be a hypergraph with vertices given by a point cloud P, and we call P equipped with H rigid if the only ways to perturb P while preserving the enclosing radius of hyperedges of Q is by isometry. Okay. And so using this definition of rigidity theory, we were able to show a theorem that a generic point cloud P is locally identifiable under check persistence if and only P equipped with its critical hypergraph is rigid. Okay, and so in some sense, we were able to find like a completely analogous result about local identifiability for check persistence. Um, One thing that we weren't able to do at all is say anything about non-local identifiability under check persistence. So this seemed something that was actually quite out of reach. So remember, we used some very technical tools from rigidity theory to say anything in the Vietoris-Rips case, and we just don't have those at our disposal because this is a new rigidity theory that we made up. Um, so uh, so as a quick conclusion, right? So we saw that like in the setting of these Vietoris rips and check filtrations, we have upper and generic lower bounds on the dimension of level sets of persistent homology, local identifiability of Vietoris rips persistence of a generic point cloud is equivalent to rigidity of its critical graph. Identifiability of Vietoris Rips persistence of a generic point cloud is implied by global rigidity of its critical graph, and local identifiability of check persistence of a generic point cloud is equivalent to rigidity of its critical hypergraph. So these were the things I talked about. Okay, so I'm all done.
Thanks, David. Can you hear me?
Yeah, I can hear you.
Are there first of all, cool talk, thank you. Um, I had a question about the global rigidity implying identifiability in the
Y-
Vietors case.
Yeah.
Are there some natural relaxations of global rigidity that give us something useful in terms of identifiability as well? What if you're happy with sort of approximate? I don't know what this would mean. I know nothing about rigidity theory, but is there some notion of approximately globally rigid that would also mean something in terms of the barcode
I
stuff?
mean, I mean, honestly, the main thing, the probably the closest thing is just regular rigidity. Right? Because that's like, um, because global rigidity is sort of saying like, I just don't just want a certain condition to hold for nearby perturbations of my graph. I want it to hold for all perturbations of my graph. Well, I guess I shouldn't all transformations of my point cloud. Um, I can't think of anything that's kind of in between the two, if that makes sense.
Yeah.
Albeit I'm not the rigidity theory expert. So Louis Theron, who were also worked on this paper, was sort of who we consulted about these sorts of things.
And just as maybe a follow-up, do you think um, there's sense in thinking about maybe there are parts of the point cloud that are identifiable, and then it rapidly becomes not identifiable when you add some more points? Is that something that's interesting to think about?
Yeah, I definitely think this is sort of true. I don't know exactly what to do about this. I'll tell you one thing that like I didn't really talk about in this talk or in the paper that's kind of true, which is that what you can do is you can use the so you get this graph on your point cloud and you can check if it's rigid to check if it's identifiable or locally identifiable, but you can also look at the degrees of freedom you have to perturb the graph without changing the edge lengths of the graph, and that tells you about the local dimension of the space. So this gives like a pretty efficient way of actually calculating the local dimension of this space generically, and this is something that I'm thinking about now. Um, is like yeah, using this for some simulations. Um, and also trying to because now what I'm kind of interested in is like what's sort of happening randomly. Like if I take a random point cloud,
Yeah,
uh, what's actually happening here. Yeah.
yeah, yeah, cool. Thanks. Yeah.
Hi there, thanks. So I kind of have two questions, but they're very similar. So I don't really have a good intuition on what this like point cloud subspace looks like. So for example, when you have your identifiable class where everything's just an isometry, what's the dimension of that space in particular? And then so like what does a basis look like for a point cloud subspace?
Okay, wait, so wait, you're just talking about like
Yeah. So first
just
is that
the space of all point clouds?
Well, the case of all point clouds, yeah, and then the
Yeah,
subspace.
yeah. Sorry. So this is the space of point clouds of n points in d dimensions. And they're n ordered points, right? So we have a notion of this is the first point, this is the second point, and so on.
Yeah,
So what that means is that it's I mean, that means that a point cloud is essentially a list of n d-dimensional vectors. So you can think of point cloud space as being r to the n times d, except that I've thrown out all the points where two points happen to overlap. Um,
yeah. Okay.
uh, yeah.
So then the
Uh,
basic vectors don't really tell you anything about the subspace. That much.
yeah. So I guess I guess before you throw out points that overlap, you could think about it as like a vector space, but I think kind of under the hood here, what's sort of more useful is to think about it is using like real algebraic geometry. Like kind of ideas from that sort of realm ended up being helpful. Like for instance, that's why the word semi-algebraic came up. Um,
So in this case where all of the point clouds that have the same resistance graph are just isomorphic to each other, or also are isometric to each other, what's the dimension of that space?
oh, that's just the dimension of that's just gonna be. I mean, if you have more point clouds than the ambient dimension. So if n is greater than d, that's just going to be the dimension of the isometry group on Rn. If you have less points than d, it's going to be I'm not sure exactly what it is. I'd need to double check.
Okay,
But the thing is that I'm actually like in some sense I don't care too much about isometry, right? That's why I'm like sort of interested in things up to isometry because we actually like that this is like 1 degree of freedom where I'm allowed to perturb my point cloud and not change the answer, and I'm happy about that.
yeah,
It's a good thing, right? I don't want that if I just like happen to translate over my point cloud, I wouldn't want that to change, what I get out of this analysis, if that
yeah,
makes sense.
yeah. But yeah, but
Or,
the dimension that you measure is like relative to like the dimension if you just do this isometry, right? So like it's like
no, no, no. The dimension I measure is not relative to that. So, oh, I see what you're saying. Yeah, yeah. So
it should
like,
be, right? Like conceptually.
yeah, yeah. So, I mean, you have another lower bound that's kind of naively given by, um, uh, uh,
Like the
the dimension of the orbit of your point cloud
yeah.
of a point cloud under the isometry group. This is true. Um, so again, if D is greater than, or if N is greater than D, then it should be the dimension of the isometry group itself. And if N is less than D, then I don't ever remember exactly what it is. Yeah.
Yeah. Another question I think about relaxing conditions.
Uh-huh.
What if you're interested not in the full barcode, but let's say you're interested in the barcodes up to a certain I, or
Okay, okay. So then, I mean, this isn't in the paper, but like arguably it should be. So let's say you're doing Vietoris rips. So then what you would do is you would basically construct a new graph consisting of just um uh, it would be just the edges that appear uh when a simplex appears and changes the I-dimensional homology. Which would be computationally a lot faster to do, by the way, if you but then the same results should hold after that. Um, so so this is something that you could do and you would get analogous results for. Uh,
so somehow the bounds get tighter and tighter as you increase the I up to which you care about.
yeah. Although it should be noted, like there's certainly examples where you can just by let's see, just by considering up to H1, you can at least in the plane. Well, maybe that's sort of disinteresting. Um, uh, yeah, that's right. That's right. Right, these bounds should get tighter. I guess another thing that's maybe worth noting is that sometimes you get more information than you need. Like sometimes you'll get a new edge and it actually doesn't decrease the dimension um, by anything. Um, uh, like sometimes like kind of persistent homology like sort of gives you redundant information as pertains to, constraining the dimension of the point cloud in some sense.
Thanks.
Yeah.
Let's just check. Yeah. Perfect. I think that was a lovely talk. Thank you, David.
All right. Thanks so much.
Thank you.
All right. You have a good afternoon.
Oh yeah, it's early morning for you, so
Yeah, I may go back to bed.
David,